Hello and welcome again to my Physics Online video lecture supplement series. Today's video is going to be a video lecture on vectors and trigonometry, which is the third set of lectures for Physics 1, and it's specifically going to be covering a couple methods for adding vectors together. And really there are two broad methods for adding vectors together that are useful for a Physics 1 class. The first is what might be called a geometric method, and this is usually done in polar coordinates. It's actually kind of shown here in this figure to the right. You could think of each individual vector as starting at one point and ending at the next, and you can see that the vectors are sort of, each one starts at the end of the previous one. And so to get the sum of all these vectors together, you start at the beginning of the first one and you draw a straight line to the end of the last one, and now you've got the sum of the vectors. Sometimes this can be called the triangle method, especially if you are doing this with only two vectors. And we'll talk a little bit more about that in a moment. The other method is to try and add the vectors together algebraically, and to do this you have to convert the vectors into Cartesian coordinates. And so you basically break each vector up into parts, x part, y part, or x component, y component, or if you go into 3 dimensions, then x component, y component, z component. So when adding vectors together graphically, or geometrically, the first step is actually to choose some sort of scale that you're going to use. And so your scale basically looks something along the lines of 5 inches equals a meter, or 4 inches is a meter per second, etc. So you're basically choosing some length of vector to represent some particular unit that you're interested in representing on the vector. So if you are adding together displacements, then your length on the scale will represent an actual physical length. If you're representing velocities, then your length on the scale might represent a particular increment of speed, so meters per second, and so on. And you have to basically pick some scale that's actually going to be convenient for you. So this is actually a skill that you also employ when making graphs. Specifically when you're constructing a graph, for example in the lab or in general, you want to graph x versus y, you have to pick a scale for the graph, and the scale may be different on the x-axis than the y-axis, and it's picked in order to both fit all the data on the graph and also to have the data taking up as much of the graph as you can to sort of maximize the little gradations you have on the graph paper. As a sort of little example of that, I have here some x time coordinates and some y position coordinates. And to the right I have two sort of hand-drawn graphs. You would want to use actual graph paper, but for an illustration this works out okay. And if I was going to plot x versus y on these two graphs, you can see that one of these two scales is not very well chosen because the y values go from 0 up to 100. And so in fact half of the values shown in this table won't fit on this graph because I've picked an increment that only lets me get to 30 here. This graph, on the other hand, the scale may not be quite as convenient for small numbers like 0 or 4, but most of the numbers on the y-axis will actually fit on the scale that's been chosen. So there's a little bit of a balancing act between wanting it to take up as much space as possible on the scale, but also trying to get the highest number possible to fit on the scale, meaning if I need to go from 0 to 100, then my scale has to go to at least 100. But if I'm only going from 0 to 100, then it's probably not a good idea to take my scale up to, say, 1,000, wherein most of the dots are going to end up down here in some lower left-hand corner. When doing graphical addition of vectors in this manner, what you're ultimately going to need, in addition to a piece of paper to draw these graphs on, is a ruler, because that's how you've determined your scale, and then also a protractor, because the vectors have to be drawn in a particular direction. So once you've done this, the other thing you should do is pick an actual start location, which will represent the origin. It'll be the start of the first vector. It's a good idea when doing this to pick an origin that is basically going to allow all of your graphs that are drawn tip to tail to show up on the same page. So if you have a bunch of graphs that start going off in this particular direction, so that you're over here in what's the gray space of this slide, then this is not a very good origin decision, nor is the scale that's been picked a very good scale. You'd have to pick an origin that's maybe more over here and a scale that's a little bit smaller to fit all of your vectors onto the page. So now once you've picked your origin and your scale, you can start actually adding the vectors, and you begin by drawing the first vector, which begins at the origin, and you have to use the correct length according to the scale you've chosen. So if you have a 10.3 unit vector and 1 unit is an inch, then you'd better draw that vector to be 10.3 inches long. You got to make sure it's in the right direction, so that's where the protractor comes in. If the vector says that it's supposed to be at 29.1 degrees, then you draw it so that you go counterclockwise from the x-axis by 29.1 degrees. If it says that you're supposed to be, let's say, 20 degrees east of north, usually this is north and this is east, so you would draw it with a 20-degree angle in the east direction relative to north. Generally speaking, the angle is taken as being counterclockwise from the positive x-axis. So what that actually means in practice is going to depend upon the context of the problem. For example, if you're firing an artillery shell, usually you take the positive x-axis to be the forward horizontal direction. And so an angle of 30 degrees or 30 degrees above the horizontal is essentially the same angle, means point your protractor so that 0 degrees is horizontal, and then move the angle to 30 degrees on the protractor. Sometimes you're given a negative angle. If you're given a negative angle, that just means go clockwise from the positive x-axis rather than counterclockwise. So basically you go counterclockwise for positive, clockwise for negative, unless the problem specifically tells you otherwise. For example, the case of going 30 degrees east of north would be a variation on that. So once you've drawn your first vector, you sort of take the end of that first vector to be the starting point of your next vector, and so you draw your second vector from there, and you repeat with the third vector and so on until you've drawn all of your vectors. And you have to be very sure that you're not changing your scale and that you are measuring everything correctly. It actually kind of helps to do something where you make a sort of new origin at the end of each vector, which looks something like this. So here's the actual origin. So you would draw your first vector starting at that origin, and I don't have a very good way of drawing on my screen in a straight line, but you'd want to use your ruler and protractor to get a straight line. You'd have some angle here, which you'd measure with your protractor. Maybe it's 38 degrees or what have you. So now that you've drawn this one, your next vector is going to start at the end of it, and so it's sort of like having a new origin that's drawn right here at the end of the old vector. And so your new vector, you'd start here. This should be a horizontal line. You'd measure your angle with respect to this horizontal line, and you'd draw your new vector at the appropriate angle. So if this angle is 12 degrees, you'd draw 12 degrees with respect to the horizontal, and so on. Then you would repeat for the third vector, wherein you have the starting point for that third vector being here at the ending point of the last one. And you would draw again with respect to your horizontal. And so off comes the next vector, and so on and so forth. So this angle right here might be 100 and let's say 30 degrees. So you'd measure off 130 with respect to the horizontal. So once you've done that, you then draw a single vector from the beginning of the first vector to the end of the last one, and then you can measure the vector's length to get the resultant magnitude, and you measure its direction with the protractor to get the resultant direction. So returning to this set of vectors that we've just drawn, if you wanted to find the sum of red plus orange plus green, you'd start your vector down here and basically draw it so that it ends up going to the end of the green vector. So I'm just a little off here because, again, I don't have a protractor and ruler that I can apply to this screen. But you would basically then have it end here and start here, and you'd measure this angle and find it to be whatever the angle is going to be. Maybe it's, in this case, about 60 degrees. And you'd measure the length of this. So maybe I've measured it as 10 inches. And if these represent a scale that says that 1 inch is equal to, let's say, 2 meters per second, then it's saying that the final velocity in this case is 10 times 2 meters per second, or in other words, 20 meters per second. So that is the geometric addition of vectors in a nutshell. The alternative to that is to do the algebraic addition of vectors. And basically the steps for doing this is that you start off with your vector given in whatever form it's going to be given in, be it polar or Cartesian, and you make sure that you break it into Cartesian form. So you have to convert from polar to Cartesian if it's given in polar, otherwise just leave it in Cartesian. And once you have all of your vectors that you're going to add in their Cartesian forms, then you can add up the components along each axis. So we're considering a vector r, which is vector a plus vector b plus whatever else, c, d, etc. So the x components are going to add together. And so the x component of the resultant vector is ax plus bx plus whatever else we're adding, cx, dx, etc. And the y components are going to add together to get the resultant y. So the resultant y, or the y component of the resultant vector, is ay plus by plus etc. So if you then want to put the resultant vector back in polar, oftentimes you'll need to, then what you do is you note that the resultant vector is rx, comma, ry, and if it's in 3D, then you have comma rz, and you can convert that back into polar from Cartesian. And so let's look at these steps one by one in a little more detail. A lot of the Cartesian method, or algebraic method if you prefer, for adding vectors together involves converting between polar and Cartesian coordinates. So to do that, what you can do is either draw each of these vectors individually using your protractor and ruler, and then measure the x and y components, or you can use trigonometry. And of these two methods, both do work. In my own opinion, the quicker, easier one to do depends upon what kind of tools you have at hand, but usually you've got a calculator, so the trigonometric method's usually going to be the faster way of doing things. With that said, you can always use a ruler and protractor to solve any vector addition question of any sort. Sometimes you have to get a little creative with how you draw your vectors and so on though. So with trigonometry, you basically want to break your, let's say, velocity vector, which has a magnitude of velocity and a direction, so 300 meters per second, comma 30 degrees, up into a Vx and a Vy. And so you take V times cosine of theta, so that would be 300 meters per second times the cosine of 30 degrees, which for what it's worth, what that's going to give you is 260 meters per second if you keep only two significant figures. So 300 meters per second times cosine of 30 degrees gives you 260 meters per second. And then your y component for this one is 300 meters per second v times the sine of the angle, so 300 meters per second times sine of 30 degrees, and so that gives you 150 meters per second. So your total velocity vector in this case would be 260 meters per second, comma 150 meters per second. So you do that for all the vectors that you're interested in adding together. So a little aside is that each component can itself be thought of as a vector, namely the ax represents the x component, could be ax comma 0, and ay, which represents the y component, could be 0 comma ay. You can actually see that from this diagram that's shown here in figure 3.2.4. You have vector A. If you want to get this vector A, you can get it by adding vector AX plus vector AY. And you can see it geometrically because you see that vector AY is beginning at the end of vector AX. And you can see that vector A starts at the beginning of AX and ends at the end of AY. So the vectors AX plus AY is equal to A. So ax comma 0 plus 0 comma ax would give us ax plus 0 comma 0 plus ay. And so that gives us ax comma ay. So with that little aside said, there's a little more trig that might be useful for us. I already kind of walked you through how to get from polar to Cartesian. So if you have vector A, you can get it into Cartesian from polar. It's specified as A, which has some length A and some angle theta. You can get it into Cartesian by taking the length A and multiplying by the cosine of theta. You could get it AY by taking the length A and multiplying by sine of theta. This still works, by the way, even if the vector ends up in some other quadrant. For example, if the vector ends up in the second quadrant, then the cosine value will be negative and the sine value will be positive, and that'll happen just naturally by putting into your calculator values of an angle in the second quadrant. So second quadrant, one possible angle could be 135 degrees. And so if you have your calculator in degree mode, you can put in that 135 degrees, and what you end up getting is that the cosine of 135 degrees is negative 0.707, and the sine of 135 degrees is approximately positive 0.707. So if you keep track of all of your sines and of your angle, everything will work out. With that said, when you want to go from Cartesian back to polar, and that is to basically do this third step, convert the resultant vector back to polar, the way that you do it is that you use the tangent of the resultant angle is AY over AX. So at this point you've figured out what the AY and the AX are. You can find the resultant angle by putting it in for tangent negative 1. And to get the total length of the resultant vector, well, that length squared should be ax squared plus ay squared. That's just the Pythagorean theorem, by the way. So what have we done here on this slide? Well, we have basically used the trig identities for sine, cosine, and tangent, and we have used the Pythagorean theorem. So at this point, there's nothing new that's going to be added in this lecture, except for that I want to work through some examples. So those of you who want to say, hey, I've got it, I understand what's going on, great. You can kind of quit for the day with watching it. For those who want to see some examples, well, that's what I'm going to do for the rest of this lecture, is work these examples and watch as many or as few as you want. So I'm going to start with some relatively short examples, and I'm going to do some longer examples. And I'm going to do a little bit of simple stuff like converting, and then I'm going to also do some actual adding of vectors, both in graphically and algebraically. So the first of these short examples is a conversion question. You have vector A, and it's given as 10 meters, 30 degrees. You want it to have this in ax, ay form. All right, so here we begin with our vector A. We want to convert it from this form, which is polar, into Cartesian form, which is basically the form that says ax, ay. So this form right here, by the way, is in a form that looks like a theta. And a word about my notation, you'll notice that I often will have these curly brackets versus parentheses. And I usually use the parentheses to denote that I'm writing in Cartesian form, and the curly brackets to denote that I'm writing in polar form. So with that said, if I want to get from a to axay, it might be helpful to begin by drawing a little diagram here. This is just a sketch diagram. If you were to draw it with a ruler and protractor, then you'd be able to draw this angle right here to 30 degrees. You'd be able to draw this length right here to represent, let's say you pick an inch equals 10 meters per second, so you draw it to be exactly 10 inches, and then you could measure this distance right here, and you could measure this distance right here to get the values for ax and for ay. Since I can't really do that very easily in the setup that I have here, I'm going to do some trig. And the trig basically is going to say that to get ax, I need to have the cosine of this angle, because cosine is adjacent over hypotenuse. So what that gives me is cosine theta equals ax over a. Therefore, ax is a cosine of theta. So that's sort of the derivation of that equation that I stated before. Therefore, ax must be 10 meters per second times the cosine of 30 degrees. Be sure that your calculator is in degree mode, because otherwise you will end up getting a wrong answer. And actually, I'll go ahead and pull up the calculator on here to show you what I mean. So on the Windows calculator, you can see that there's degree mode or there's radian mode, and I can put the calculator in either. If I put in degree mode, what I have is 10 times the cosine of 30. And the way I have to enter these, by the way, number first and then hit cosine, and I get 8.6. And if I put it in radians instead, I would have 10 times the cosine of 30 degrees in radians, and I get 0.15. So you know that if the angle is 30 degrees, that cosine of 30 degrees should be equal to square root 3 over 2, and that sine of 30 degrees should be 1/2. Not really sure why the computer is putting these little lines in here as I drew this, by the way, so very sorry about that. In any case, what this gives us is that AX is approximately 8.7 meters per second. Alright, and then similarly, sine of the angle theta has to be opposite over hypotenuse, so that's AY over A, and so that means that AY should be A times the sine of the angle, and therefore AY should be 10 meters per second times the sine of 30 degrees. Sine of 30 degrees is again equal to 1/2, and so this ends up being 5.0 meters per second. So the final answer then to this example is that A in Cartesian form is 8.7 meters per second, comma 5.0 meters per second. So there answers the first of these short examples. Let's move on to the second one, therefore. Second example wants us to do sort of the opposite of what we just did, which is to convert vector B from Cartesian to polar coordinates. So vector B is in Cartesian coordinates is 6 meters, comma 8 meters. So what does this vector actually look like, by the way? Well, let's go ahead and draw for ourselves another sort of graphical depiction of it by drawing out an origin with a pair of axes. And basically, if you had a ruler, you would take it and you draw one line that comes along here that is 6.0 meters long. Then you draw another line that comes up here that is 8.0 meters long. And then to get the resultant vector, you draw one from the start of the first to the end of the latter, and then you could measure this angle right here, theta, and you could measure this length right here, b, if you've drawn everything to scale, and so be it. Now you have it in Cartesian. If you're going to do the conversion, though, mathematically, what that looks like is that the tangent of the angle theta is equal to the opposite, which is by, over the adjacent, which is bx. So you'd have by over bx. And so therefore, to get theta from this, you take the inverse tangent of both sides, and you have by over bx. So if I was going to plug numbers into that, what theta ends up looking like is the inverse tangent of 8.0 meters divided by 6.0 meters. So pulling out our calculator, you have 8 divided by 6, and then we want to be sure we're in degree mode. We click the inverse button, and here is the inverse tangent, and it says it's 53.1 degrees. So at two significant figures, this is about 53 degrees. Okay, the other thing that we got to do is get b, and you can see here that b squared is bx squared plus by squared. So if you want to get rid of the squared here, we take a square root of both sides. And so b must be equal to the square root of 6.0 meters, quantity squared, plus 8.0 meters, quantity squared. So this right here, 6 squared is 36 meters squared. This right here, 8 squared, should be 64 meters. That's a 4, not a 9. So 36 plus 64 means that b is the square root of 100 meters squared, or in other words, b is 10 meters. And so if we want to get the vector that is represented by these guys, it would be 10 meters, comma, 53 degrees. So in other words, if you were to go with your meter stick and your protractor and measure this angle, you should get about 53 degrees, and measure this length and you would get about 10 meters. Okay, the last of the actual short examples says that we want to add vectors a and b from these previous two examples together. So what would that end up looking like? Alright, well, the two vectors in question, a and b, are given here. I think it's going to be easier for me to just add them in Cartesian, especially because this little sketch pad that I'm working on has a tendency of blurring things and is not actually the screen that you see. So for me, I'm just going to go with the Cartesian set, and I'll show you a geometric in a example that you'll see shortly. So if I want to do a plus b, I can do ax plus bx, and what that ends up looking like is 8.7 meters plus 6.0 meters, and that gives us 14.7 meters. And similarly, there is ay plus by, and what that's going to give us is going to be 5.0 meters plus 8.0 meters, which is going to give us 13.0 meters. So we end up with, therefore, a total vector, if we wanted to put it in terms of in Cartesian terms, we would have 14.7 meters, comma, 13.0 meters. And if we wanted to put that in terms of polar, you'd basically have to use Pythagorean theorem to get the hypotenuse, or in other words, the total magnitude. And so what you'd end up getting for that is actually about 19.6 meters. And so your magnitude here ends up being 19.6 meters. And then to get the direction, you'd have to use the inverse tangent of the y part, which is 13 meters, divided by the x part, which is 14.7 meters, and you'd end up getting 41.5 degrees. That is your vector in both Cartesian and in polar. Alright, so at this point I wanted to do a slightly longer example because I want to do one where we add the vectors up geometrically. So here are the vectors that we want to add together: A, B, C, and D. So what would this look like if we were going to add these together geometrically? So I have chosen a scale. This length right here is going to equal 10 meters. And I'm going to color code it. So the first vector that I'm going to draw is vector A. By the way, my origin is going to end up down here. So vector A has been drawn. It is 10 meters long. It is in the 45-degree direction. Now I want to draw vector B. So vector B is 5 meters, 180 degrees. So this is 5 meters long. 180 degrees means pointing along the negative x-axis. Now to that, let's add C, which is 15 meters in the 90-degree direction. So this right here does in fact represent 15 meters. 90 degrees is straight up. And then the last one is 5 meters, comma 30 degrees. So 30 degrees is this way, 5 meters is this length. So now I've drawn my 4 vectors. I can now add them all together to get the resultant. So I should draw a black vector, according to my color scheme, a black vector starting here and ending here. So that would be this. And to get the length, I use my measuring scale. And it looks like, to me, we have 5, 10, 15, 20, 25, maybe about 26 meters. And then we can measure this angle to get our final answer, 75 degrees. So 26 meters, comma 75 degrees. For what it's worth, we could also break these up into components geometrically. So I've drawn each of these vectors again sort of independently, each one starting with its own origin, and can then break it up into components by drawing an x and a y part and measuring them. So in the cases of B and C, it's really easy because they're already sort of broken up into those components. This one is negative 5, comma 0. This one's positive 15, is 0, comma positive 15. The other vectors we would have to break up by measuring the lengths ax and ay and dx and dy. And then you could add them algebraically by doing ax plus bx plus cx plus dx and ay plus by plus cy plus dy. And what you'll end up getting if you do that and then convert back to the polar form is again 26 meters, comma 75 degrees. So that's all that I wanted to cover in today's video. I hope you found this helpful, and these are sort of the sources where I've pulled a few of the figures from. Anything that isn't listed here in my reference sheet is something that I made myself. So you know, credit has been given to the people who have made the original graphs that I've used. In any case, I hope you found this video helpful, and thanks for watching.